All right, today we are diving into a really clever concept in software design, application-driven fault tolerance, or ABFT for short.
So just imagine for a second. What if instead of an entire system grinding to a halt because one little part fails, your application was actually smart enough to just fix itself and keep on going? That's the powerful idea we're digging into today.
So here's our roadmap. First, we'll talk about why failure in big systems is, well, inevitable. Then we'll compare generic versus specific recovery methods. We'll define what ABFT actually is, look at its strategies, see a real-world example with linear algebra, and finally wrap up with why this whole concept really matters. Okay, let's jump right in. First up, the inevitability of failure. It sounds dramatic, but there's a reason why large systems are pretty much guaranteed to break. So to set the scene, think about how we build these massive distributed systems. We're pulling together computing resources from all over the place, sometimes from different parts of the world, all to work together on solving incredibly complex problems.
And these systems, well, they face a ton of threats. We're not just talking about a hard drive giving up. There are malicious attacks like denial of service, system intrusions, data theft. And of course, you've got your everyday hardware failures and simple human or machine errors. It's a tough world out there for an application.
Now this gets to the absolute core of the issue. As you add more and more processors to a system, the chance of something failing doesn't just go up a little, it rockets towards 100%. The key takeaway here is that failure isn't an if, it's a when. For big enough systems, it's a statistical certainty.
Okay, so if we know for a fact that things are going to break, the next question is, what do we do about it? And are all recovery methods created equal?
So let's think about that. When things do break, what's the typical way systems handle recovery?
Well, the traditional method is often a kind of brute force approach called system-level recovery. A good way to think about it is like a system-wide save game. If one single part fails, everything stops, and every process has to roll back to the last good checkpoint. It's a sledgehammer. But there's a more surgical approach, application-driven recovery. This is where the application itself is smart enough to use its own knowledge to perform a much lighter, more targeted fix on only what broke.
And that smarter, more specific approach brings us right to our main topic today. What exactly is ABFT? It's all about putting the application back in fault tolerance. At its heart, application-driven fault tolerance is really all about this: using the unique knowledge an application has about its own data and its own logic to create a custom recovery plan. Instead of a generic one-size-fits-all protocol, it creates one that's way more efficient and lightweight.
Now that sounds great in theory, right? But how does an application actually do this? How does it fix itself in the real world? This is where it gets really clever. An ABFT-enabled app has a playbook with a few different options. First, if its data is redundant, meaning it has copies or can recalculate it, it can just reconstruct the lost data and keep on going. No big system-wide rollback needed. If the data isn't redundant, it can make a strategic choice. It might decide to just continue the job with the processes it has left, or it could spawn brand new processes to replace the ones that failed. The important thing is the application itself makes the call.
So let's make this more concrete with a real-world example: linear algebra kernels. A perfect, classic example really does come from the world of linear algebra. See, a lot of those algorithms naturally have redundant data built right in. Because of that, you can add something called a checksum, which basically lets you recompute any lost data just from the pieces that survived. The application literally uses math to heal itself. A great way to think about this is that a checksum acts just like a mathematical receipt. You know, if you lose an item from your shopping bag, the receipt has enough information for you to know exactly what's missing. It's the same idea here. The checksum allows the application to use the remaining data to perfectly recalculate the piece that was lost in the failure. Okay, so let's pull all this together. Why does ABFT really matter? What's the key takeaway here?
Well, the advantages are huge. You get lighter protocols, which means less system overhead. You completely eliminate that massive disruptive need for every process to stop and roll back. Recovery is targeted. Only the affected processes need to do anything. And when you add all that up, you just get a more efficient, more robust system that performs way better under pressure.
If you found this explainer helpful, please do us a favor and like, share, and subscribe so you don't miss what's next. And we'll leave you with this to think about. As our systems get more and more complex, and failure becomes even more of a certainty, Do you think these self-healing applications will become the rule and not the exception? Thanks for tuning in.